We'd like to talk about coordinate systems and underlying them, datums and map projections. So we usually work in two different kinds of coordinate systems, and we, in our GIS, use a planar system. So you see the little green rectangle here. That's our vision of a layer in a GIS, and it's a flat layer. It's a Cartesian layer. And it basically has a north and an east direction and then up out of the Earth on a line that's more or less normal to the surface of the Earth. So this is our GIS view, but we have to resolve that on this spherical globe, or approximately spherical globe, on which things are placed. Now, in most GIS analyses where we want to pay really strict attention to areas or distances, we have a fairly small area, not near as large as this rectangle shown here, but it's tangent to the Earth and has this east and north direction for our system. And so we have this planar view of the world. We might think of it in this old drawing as a plane table on which we map things. And working over small areas, that's fine. We can establish a Cartesian system, and we can have an x-axis and a y-axis. So here, these x direction and y direction, they meet at right angles everywhere over our area. So there's this right angle or 90-degree junction for the x's and y's. And all of the lines more or less point in a north direction. This isn't exactly true, and we'll describe this in detail when we get into the map projections portion, but for right now, just think about this Cartesian coordinate system. The thing is, we can't use a Cartesian system over large distances, and since all our measurements really come back to finding where we are in a latitude, longitude relative to an origin, a 0, 0, a long way away, we use spherical measurements of a longitude and a latitude, and a r, or radius, from the center of the Earth. Now, these are called spherical systems. Special kind of sphere is an ellipsoid, or I should say a sphere is maybe a special kind of ellipsoid, because in a sphere we only have one radius. The Earth isn't shaped like that. As I'll talk about later, as it spins around, it flattens some, so the poles get pulled in, and the belt around the middle or on the equator gets thrown out a little bit. So the rotation of the Earth actually deforms the Earth into something that's non-spherical. But a spherical approximation is pretty good for coarse measurements. And we'll get into the details of the ellipsoid, which has two different directions later. Right? Why are there 360 degrees in a circle around the globe? So we have 360 degrees in the equatorial direction and also in the direction of the poles. And why 60 minutes in a degree and 60 seconds in a minute? Well, it basically, like many things, comes from a convention established thousands of years ago when folks first figured out how to deal with geometry. The Sumerians were very practical people in many ways. They had engineers that realized, look, if I had a radius here that was from the center of a circle out, and I could get that radius pretty easily, right? I could put a post in the ground and draw a circle with a string or another stick, and that was the distance. I could lay roughly six posts in between around the circle, and so I then could get 6 of these, and that's sort of a base 6. They also realized there were about 360 days between the equinoxes, so they split a circle into 360 parts, kind of a base 10, graphed it onto this relatively useful method for identifying distances around a circle. So they split things into 60ths because they had this 1/6 they could measure, and then that into 60th again, just to stay consistent. So we go from 360 to 60th to 60th. So we have degrees, minutes, and seconds, and we've just carried that convention along. There's no reason we couldn't at some point have decided we're going to have 1,000 or 100 degrees, and the degree would be a different size, but we didn't, and this is the convention we carry forward. The latitude-longitude system is not Cartesian, and you know why. The lines here in the north-south direction converge to a point. They're not parallel. If they were parallel, they would never meet, and here they all meet. Now you've seen graphs where they cut this and unroll it and show these along the top being parallel. That's a bit confusing because that line across the top, they all match to this one point at the North Pole, and the one at the bottom to the South Pole. Now on the surface of the Earth, we want to measure distances as a great circle distance. We can measure any distance from anything, but a straight line has a different definition on a curved surface. And so this great circle distance, if we know the radius and an angle, we can get the distance d. So I have the radius from the center of the Earth out to the surface, and I know how many degrees I've traversed. Well, I can get the distance. And we often do these calculations in these radian measures in geodesy, in the study of the curved surface of the Earth. Well, what is a great circle? It's a circle on a plane that goes through the center of the Earth. So there are an infinite number of planes. All they have to do is hit this point, so I can pivot this around. And the great circle distance is always the shortest distance on the surface of the Earth. And that's typically what we think of as a distance, the shortest distance in a Cartesian system. We use the shortest distance. It happens to be the straight line between them. But straight is different on a globe. And if you look at the globe from different perspectives, these straight lines seem curved because you're not looking at it from the right direction, right above it, on top of it, where you're basically directly above this great circle. Now, the great circle always splits the Earth into two halves. And you have a complement to the great circle, which is a small circle. The small circle splits the Earth, but it doesn't go through the center. And so it doesn't split the Earth into two halves. It splits them into a bigger piece and a smaller piece. Again, we always want to measure distances in the great circle, right? So as you have a problem, you have historical field observations of land cover types in Minnesota with lat-long coordinates specified to the nearest 10 seconds of arc. So a lot of folks collected data and used relatively coarse measurement means available to them 100 or 150 years ago. And so these data are mapped, like the public land survey system, every chain or two chains or quarter section or mile, or in this case, it's in sections of arc they're reported, so 10 seconds of arc. I have a present-day satellite map at 1 kilometer resolution. How we combine these depends on the resolution of the two maps. We don't want to infer too much about the location of things if one of these is a much higher resolution, a much finer resolving power. So I can see small stands in one, but only coarse stands in the other. I really can't do a comparison at that fine stand level. So we have to calculate which of these has a higher resolution, which means what is the surface distance of this 10 seconds of arc, right? It's a perfectly good example. Here's the, I think, early General Land Office survey derived maps where people surveyed the land running the land lines north, south, and east, west, and they recorded every quarter mile the vegetation. So we have a map. If we look at this and can say, look, they're consistently going through a hardwood type, we can map this as hardwood at the time and then infer around the edges. And here's a 2011 land cover map from the Landsat satellite system. So which these has a higher resolution, right? Well, we know the radius of the Earth up to Minnesota, and we know the angle here, right? Theta is the angle. One radian is 57 degrees. This is the Earth's radius, so it's 10 seconds of arc. Well, right, 10 seconds of arc divided by 3,600 seconds in a degree, divided by a degree equals this many degrees, right? And so with that many degrees times 57.2957 degrees per radian, I have this many radians, right? 4 zeros point, and then a 48481.435. So if I multiply by this equation, the radius times this angle, and notice the angle I always have to convert to radians, I get 309 meters. So one has 309 meters, and that's a much higher resolution than the 1 kilometer. So the old data are actually at a higher resolution than new data. I could get new data at a higher resolution to compare to these, right? We have to be careful using these formulas because they're only accurate along great circle distances. So I have a series of locations here: Libreville to Nyasaland, Cozy Corner to Genoa, right? Nyasaland to Quito, And so the great circle distance for this formula works. The non-great circle doesn't. Right? This is a small circle because the lines of equal latitude are not great circles except at the equator. All the lines here, the lines of equal longitude, are great circles because they go through both poles. The latitudes don't. So I have to be careful in using this formula that I apply it correctly. Like, this is not valid because it's a small circle. It subtends this line. It's great for an approximation. In the book, and later on, we talk about closed form, more accurate solutions for any coordinate pair that we have. But this is good for just rough estimates along great circles or for small distances. Okay? Remember great circles and small circles. And again, as this says, this is not a great circle. We have to realize that. These aren't actually great circles, but they're pretty close to great circles because by the time we get up here to the Svalbard Islands, we're practically up in at the pole. And so this is pretty close. Imagine living there. I mean, we can't complain about winter here. Think how long their winters must be that far north. And one of the things that's caused real issues in datums is that all coordinates are measured, and so they all contain error. And as the measurements improve over time, we get better estimates. Well, if we spent a bunch of time creating maps with the poor measurements, when we create new maps using better measurements, things are going to shift around because I might have made a mistake in a distance. In the old days, when all measurements were local, you could use things like piles of rocks to say where a property line was, and as long as somebody didn't systematically move the piles of rocks, there weren't any disputes. But if you're starting from a location far away and measuring distances to get to locations, these lines might end up giving you a different location by the time you get to the end of it, depending upon how well you measured. So the most accurate measurements of latitude and longitude today, we ask a question. They're actually these galactic radio waves. There's a series of these very long baseline array star measurement observatories. There's, over 100 around the world on various continents, and they can give us millimetric estimates for locations as the Earth spins around the sun and as the Earth rotates itself and as the plates move across the planet. So this is by far the most accurate, but it's so expensive we only have it in a few places. We use astronomical surveys and GPS, and we used to use ground surveys to extend those really accurate measurements. So this new technology allows us to locate things very effectively. These old methods, we could get distances across the country to within a few tens of centimeters, a few half a foot, something like that. But now we can do millimetric accuracies. The one thing that's really confusing and has caused a lot of consternation is that the plates are moving. So if we have old measurements and we want to integrate them with new measurements, we basically have to integrate this knowledge of the movement of the plates. In the olden days, before they knew about plate tectonics, they thought the idea was, well, if we measure carefully enough across a continent and then measure to stars using optical instruments and measure carefully enough across another continent, once we had everything measured, we'd be done. We could say, yep, I measured everything as fine as I can. We don't need to do any more mapping except for things that change due to landslides or earthquakes or things moving up and down. But in the 1960s, they became pretty convinced that, there's unequivocal proof that the plates are actually moving. So that old idea of mapping a static map no longer was valid. And so really they started looking for their technologies between the 1980s and the mid-2000s. They developed technologies for measuring where things were effectively on the Earth. Right? The measurements have gotten so good we can assimilate continental drift into our coordinate systems. And so we have to basically timestamp our sets of measurements. Our sets of measurements, when we calculate where things are, we call a datum. It's a reference surface against which we measure things. And so if I'm on this side or this side of a fault, I can fix that into my datum and tell you which shift I have to account for. If I have old data before it shifted and then new data after, I can assimilate those data. I can combine those data because I can say, well, how much was the shift over time? I can incorporate continental drift. There's another confounding thing. Our Earth isn't shaped like a sphere or an ellipse. Earth is lumpy. And it's lumpy because there's different densities in the Earth and materials below the Earth. And then also there have been glaciers 2 miles high resting on the surface of the Earth, and that's pushed the Earth down in places. So we get these different heights of the actual surface of the Earth, and we call that a geoid height. Now, it's not the actual surface that we're measuring, the geoid height. We're measuring a theoretical surface if the Earth were covered completely with water and nothing disturbed the water like winds or tides. So where would that rest? What's the theoretical sea level across the surface of the Earth? And it is quite lumpy. Now, this is a great exaggeration. You couldn't really see the lumps at this scale, but they are pretty substantial. They're on the order of 200 meters, so something like 600 feet from the highest to the lowest. So there's an area here in the Indian Ocean that is lower, that's pulled in, and an area up here in the North Atlantic that's pushed higher than the regular surface of the Earth. And so we had to be careful when making measurements and then realizing there was a geoid in the 60s through the 2000s to incorporate this into our estimates of where things were. Right? We had an original survey network in the 19-teens, and then we updated it in the 1980s. And it was this static idea. But while we were updating it, we were also developing these methods for measuring things more accurately using GPS and that very long baseline array with networks of GPS tied to that array, that we had this period between the 80s and the 2000s where we came out with multiple datums because there were multiple iterations of figuring out where things were, of incorporating tectonic movement. Right? A lat-long measurement is made on the surface, but it's reduced to an ellipsoid. We typically establish a standard ellipsoid that is a mathematically defined surface that fits as best we can, in a least square sense, this geoidal surface. And then we project every measurement we have on the surface down to it. Okay, we have an origin here into the mass center of the Earth. We have an ellipsoid, and we're projecting down onto it. The best estimates of the ellipsoid have changed as our measurements have gotten better. So every time we do a change in the ellipsoid, we have a new datum, a new surface. A datum specifically defined is this surface, an established mathematical surface, plus a set of measured locations reduced onto that surface. As I'd get more locations and measure more places, get a better estimate of where this surface should sit, I might have a different origin, a different shape, and I'll estimate new locations. They shift slightly between one datum and the new improved datum. So we have to be careful that we know which datum we're using. And then with that datum, we can project, which I'll talk about in the next lecture, from this curved surface with this set of locations onto a flat surface. Right? This satellite computer revolution, basically the VLBA plus the GPS plus the ability to compute these new datums quickly changed the way we go about thinking about datums and coordinate systems. And we had this period of about 20 years of rapid updates of datums. Instead of updating them every 60 or 70, 80 years, it was every year or 2 or 3. Unfortunately, that's when GPS came on. When GIS came on, and so we have this real confusion in datums and layers and coordinate systems during that period of time. Right? Here are 2 different ellipsoids, right? I'm getting a different origin for ellipsoid A and ellipsoid B. The first ellipsoid might have relatively few points, right? This 0.5 and 0.1, and so we think this is the best fit. The second ellipsoid, ellipsoid B, we measure a bunch more points. It fits better to this set of locations, and so the origin shifts and the radius might change. Certainly the radius in both directions changes. So these two different geoids give me different locations on the surface of the Earth. The North Pole isn't going to be in the same place. If this is the physical North Pole, it's going to apparently shift when I go from one to another. And this happened when we were improving our datum. So this WGS84 has one origin and location, or the ITRF, which is aligned with the WGS84, and the GRS80, which we are using now but will soon abandon, shortly update, have a different origin. So in the US, we have one datum, and the rest of the world, they have another. It means coordinates are in different locations, right? Lat longs, when reduced to different surfaces, this ITRF and WGS84 or the NAD83, occur in different locations. You get a shift in the latitude and longitude. And so you get a shift in the coordinates of these points depending on which datum you use. That's why when we look up Control Surveyor, when we get coordinates for points, they're sometimes different. It's because they use a different datum. Right? This uses something called the NSRS 2007. This uses the 86 and the 96. And again, the reason we have different datums is because this new technology came along with the realization that the continents are shifting. And so we developed rapidly over 2 decades an ability to measure and then applied that and got better models and better estimates of the coordinates of things in the datum and the shape of the Earth. So if you look at our estimates of the same point, the point itself hasn't moved, right? A control point named Bloom 1 in New Jersey, one of those monumented, well-defined points. From where we thought things were in the 1927 datum, and we used this up until the early 1980s, to where we measured it in 1986, there was a almost 40 meter, 100-foot shift in our estimates of the location of the point. The point didn't shift, just our knowledge of where it was relative to the latitude and longitude system changed. And then, again, in this period, the Horn was in 1987-8, the CORS 96 was in 96, the NAD83 in SRS 2007. So all of these are shifts in locations that are due to improved measurements, right? So the first one was because we had a lot better network, and so we had 100-foot, and then these are 4 centimeters, 5 centimeters, so a couple inches. But remember, these are all using one ellipsoid in one location, because this other ellipsoid, the WGS84 ITRF, uses another location. They've actually updated the location. There's about a meter difference between them. So these differences within the NAD83 family are increased measurement accuracy, but these are just different conventions. There's a 3-foot offset between how the rest of the world measures location and how we do. Now, there's a bunch of complicated reasons, but the primary one is that we didn't want to change the locations too much within this NAD83 family to confuse the surveyors or make them have to go all adjust their coordinates in the US because we switched datums. But it's gotten to the point now where everybody's using GPS. It's relatively easy for them to calculate new locations, so we will switch to something compatible with the rest of the world. The rest of the world was a little behind us in the adoption of these dynamic geodetic datums, and so they just said, look, we're going to all switch to this ITRF, this standard location that we can then pool resources to measure better. Now, it's not bad that we're using these two different systems because we can always convert one to another. It is bad because if you don't pay attention to what the datum is, your data may line up by or misalign by a meter, and that happens quite commonly, meter and a half. So our coordinates change with each different family of datums from the NAD83 to the ITRF, and our datums have changed through time with each family as we get more and better datums, right, as things improve. Now, I put together in the book the 3 main families in datums. There was nothing like this at the time to try and help people understand, right? Here I'm improving the quality of the measurements. And so from the NAD83-86 to the NAD83 Horn, This is non-GPS to GPS. We have a meter shift. And then from the Harn to the Cores 96, again, this is the next version, 5 to 20 centimeters, so 2 to 8, 10 inches in the positional locations of objects that haven't moved. And then from the Cores 96 on, they're generally less than an inch, the shifts. So these have really gotten stable as we figured out how to use the technology. The WGS84 and the ITRF are datums used by the rest of the world. This was started by the US military, but they aligned theirs with the ITRF after a few years because they want to map things everywhere on Earth. And so the ITRF was first established with the best data possible, and their shifts between each of these are a few centimeters. They're basically increasing accuracy and then measuring continental drift. And so they change things slightly because the measurements have improved and because continental drift in an odd way makes things shift a little bit. They're averaging the continental drift across all continents. So you might say, well, why aren't the shifts bigger than that? On average, they sum to near zero, but individual points may move bigger than this few centimeters. So there are tools for converting between these two different datums. If I have data in the NAD83 and I need it in the ITRF, or if somebody gives me data in the ITRF from a European satellite system and I want to bring it into NAD83, I can use a mathematical equation that will go, if it exists, from one datum to another. Now, often they don't exist for all of these. For example, there isn't one from the NAD83 and SRS 2007 to all the ITRFs. You'll go to one ITRF, and the ITRFs, there's conversions between them. Within the family of datums, every time you come up with a new version of a datum, you back calculate the projection transformation, I shouldn't say projection, I say the datum transformation to go back to previous datums. So I can always apply systems of equations, mathematical functions to go within the family from any datum to an earlier datum or from any datum to a later datum. And a few of them, they calculate across families. So I can go up and down the ITRF chain, and a few of them I can go across. So I might have to go from this datum transformation to this one, and then this one across to this one, and then this one down to another one. So I can go back and forth. That's what this software does, this HTDP. It's a time-dependent positioning tool that the NOAA developed. There are other ones that you can get within various other softwares, but we need to go from one datum to another because our data have a different base if they're in different datums. If you're not in the right datum, you may be off by a few inches to 6 feet unless you go to a real early datum when you're off by hundreds of feet. So we can do a datum transformation, and this datum transformation can happen when we do the map projection, or we can do it in that software like NADCON, HTTP. Well, what is a datum transformation? It's a conversion from one ellipsoid to another ellipsoid. I first shift the origins. There's a delta x and a delta y to shift the origin to a new location. I scale if there is any scale change. So I'll multiply every z by a little bit more or less to change in distance. And then I rotate in 3 directions, the x, y, and z, around the x, y, and z axes. So I can go from any datum to any other datum, provided these equations are given to me. And that's what I said when I do some of this calculation. It's a datum transformation that goes from the NAD83 Cores 96 to the 2007, or from the ITRF 0 to the ITRF 94. So I'm using datum transformations all along to figure my way through. It looks something like this, right? You have to tell it what's the input, and it'll tell you, here's a WGS84. It's going to use the ITRF 2008 because they're the same thing. And I want to go to an output, the NAD83, 2011, 97, 2007. Now, why are these all the same? It's because the transformation doesn't distinguish between them because the accuracy is less than the difference. So this might be 1 centimeter difference between this, the 2011, the Cores 96, and the way they fit these transformation equations, it maybe isn't accurate to within a centimeter. So they just say, oh, well, they're all the same as far as we're concerned, right? You can use that table I showed, this figure, to answer questions about when you do or don't have to do datum transformations. because it's a bad habit of people that know their data well and have worked with it a lot to not do a datum transformation, even if the data are in different datums. And the reason they do that is because it doesn't make a difference. The datum transformation difference, right, let's say from the Harn to the 2007 might be only 10 centimeters, but if their data are only accurate to the nearest 5 meters, who cares? They're not going to be mapped at a resolution better than what the datum transformation is going to move things. So it's saying, look, I don't know where anything is to the nearest 5 meters, 15 feet, and yet you wanted me to do this whole processing step that shifts things 8 inches? I don't think that makes any sense, or 4 inches or 6 or whatever the small amount is. So you'll see people not doing datum transformations and getting away with it, and then they don't do it and they get screwed, messed up, lousy data. It's because they cannot do it, they can avoid it, they can ignore it when their data are coarse. As their data gets better, they can't ignore it. And our data are getting better and better with GPS. It's real easy to get inch-level data or 2-inch level data now with relatively inexpensive receivers and not that much time in the field, right? So what we want to do is answer the key question. You should have an inkling of the key question. The key question is, what is the difference in this datum untransformed? What's the error if I ignore this? And then is that much bigger than 10 centimeters, right? Is the datum difference near the magnitude of the data accuracy? I'm saying, look, the transformation from one datum to the next, how much of a cost do I pay by ignoring it? And that's here in this figure, right? Typically 5 centimeters, but up to 20 centimeters. So this is a meter. So from this down to any of these is going to be a meter, right? A meter to 2. Whereas 2 centimeters to these are all a couple centimeters apart. So I don't need to pay attention to that difference if the data are coarser than that, right? So here's NAD83 Harn, NAD83 2007. If I look at this figure, where I'll do the NAD83 Harn to NAD83 2007, 2 centimeters, this is 5 to 20 centimeters. And it asks, well, 10 centimeters, yeah. The 5 centimeters is the datum transformation. If that's all the difference is, I don't have to worry. But if it's 20, if the datum transformation is 20, basically the data transformation error will screw up my 10 centimeter data. So I really can't ignore it. I have to do that datum transformation, right? How do we perform this in Arc? Well, you'll go through that in lab, but use the project command. And the project command allows you to pick the input and the output, right? So the NAD83 2011, and this is for a particular coordinate system. We'll talk about that in a bit. And this is the 83 to 96 to NAD83. So we have different datum transformations we're doing here, right? From the 2011 to the 96. So that's in here, right? I can pick those, right? Sometimes you need multiple datum shifts. Remember, sometimes there isn't a transformation from here to here. Sometimes I have to transform down a couple and go across and then go down or up to get my proper datum transformation. I'm actually applying several, one from here to here, then one from here to here. So if you look at Arc sometimes, you'll get these multiple column transformations where they'll talk about there's this one plus this one. There isn't a direct one from the Harn to the Cores 96, right? They'll have to go through some intermediate one to get there. So they do a pretty good job of picking their way through these published transformations. You got to be careful in Arc, like a lot of things. They sometimes hide things, and you have to know that there's a modifier in here for all the transformations except for the original NAD83 1986. They say, well, that's NAD83. And having been around long enough, I know the reason this is structured as such is, first there was only the NAD83 1986, and as they added new versions, the 96 or 2007 or 2011, rather than fix this and put an 86 around it, they said, well, we'll just start a new folder and add these into the new folder, the 96 version or the 2007 or 2011 version. So those all show up here, but they don't show here. And the bad thing is people will sometimes look for the projection, see, oh, I want entity 83, that must be where it is, look in here and not find the various versions and say, well, I guess it doesn't matter, and pick the coordinate system they want, but they're picking the 86 version when maybe their data are in the 2011. So you can get in trouble without knowing that that's a landmine or a trap in ArcGIS, and make sure you know that they have the version supported. Right? For modern 83, make sure you have the year modifier if you can find the date and the area. So you need to now pay attention to the time of collecting your data and then what projection it went into, what datum transformation you used to go from the spherical system or map the spherical system on the surface of the Earth. This is important when we go to projections, but right now, just to know what you're measuring as your zero or starting point. So you need to pay attention to these modifiers, right? If it's ITRF or it's at entity 83 2011. So you need to know what the modifier is for your datum. Again, remember, a datum is a set of points mapped on the surface of the Earth and the coordinates that go with them. And if we have different geoids, we're going to have different coordinates and hence different datums. And we need to use the datum transformation to go from one datum to the next, irrespective of, even if we're staying in the same Cartesian coordinate system. So, hope that helps.